Good morning, everyone. My name is Min Kai from Taipei. Thank the organizers for giving me the opportunity here to share with you a pet project in collaboration with Maris Lehman, who was my postdoc, has now moved to the States. I want to start off with a statement that's probably so obvious that we don't even think about, and it's the fact that protoplanetary disks are dominated by gas, and therefore whatever happens with the gas dynamics should have a profound impact on all stages of planet formation and evolution. One of these issues is turbulence, because the gas in the disk is probably not sitting there quietly. There's probably some level of turbulence, and turbulence can be a double-edged sword, because on the one hand, of course, you have turbulent stirring of particles. That's detrimental to planet formation. But disk turbulence can sometimes also reorganize itself into large-scale structures, like pressure bumps or vortices, which can actually help to collect dust grains and help planetesimal formation. So the reality will be a competition between these two effects. Now, in the literature, you'll find an endless list of instabilities, hydro and HV instabilities that can drive turbulence. I've listed 3 examples here. Vertical shear instability has been studied quite intensively in the last few years, and we actually heard about this earlier this week, and also I think there are a few posters on this. But I'll be focusing on something called the convective overstability. This is essentially a form of convection, but in the radial direction of the disk, towards and away from the star. And let me just explain how it works. Now, to good approximation, disks are Keplerian, and Keplerian orbits are stable. So what would normally happen if you were to perturb a fluid element in the disk is that it would just oscillate around its mean orbital radius. But now, if you allow the fluid element to exchange heat with the surroundings, what could end up happening is, as the fluid oscillates into the inner hotter disk, it would absorb heat from the inner disk, it would expand and experience a buoyant acceleration and overshoot into the outer disk, which is cold. And then it would actually lose heat to the surrounding cold material, contract and sink back down and overshoot into the inner disk. And the cycle can actually spiral out of control, and you have instability. Now we can work through the details, and at least in this midplane, you have a relatively simple criterion where for the instability to operate, you need the entropy to decline with radius. It's actually not a typical situation, but if that does happen, you have instability. Off the midplane, things get a little bit funny, but if we're in the midplane, we have this relatively straightforward criterion. And also, if you want this convection instability to happen on an interesting timescale, the thermal timescale of the fluid should be comparable to the dynamical timescale. Because if the fluid was isothermal, then there is no buoyancy effects, so no instability. But in the opposite limit, where the fluid is adiabatic, there is no heat exchange, and therefore no instability. Now, provided these are satisfied, you have a system that is dynamically unstable, meaning if you give it a small perturbation, it would grow exponentially in time and saturate to some amplitude. These are simulations using 2 different formulations of the same problem: a compressible model simulated with the Etafix code, and a incompressible or Boussinesque formulation of the problem using the Daedalus code, which I'm a big fan of, by the way. And what's plotted here is the radial velocity perturbation. So you have this exponential growth. It saturates to some amplitude, typically say 10% of the sound speed. So then the question is, what happens in the saturated state? Because you have this turbulence, but also potentially structure formation. So which one wins? Are the turbulent kicks going to win, or are the large-scale flow structures going to win? And as with a lot of things in life, the truth is often somewhere in between. So I'll just give you a demonstration of what might happen. So this is a movie I'll play in a minute. What we're looking at here is the dust density. The dust is immersed in the gas. The gas itself is undergoing this radioconvective instability. And we're going to be looking at the evolution of the response of the dust to this convection instability. So let me play it. So as you can see, you do see some particles stirring initially. Particles are stirred around, but over enough time, over the simulation timescale, a couple of hundred orbits, you see the formation of dust rings. And that is because the gas in the background is now slowly forming what we call zonal flows or pressure bumps. But the key point here is that if I can try to play it again. But the point here is that this trapping process is very unsteady. these dust rings are highly unsteady, and the dust-to-gas ratio I can achieve is at most a couple of times larger than the initial value. So I end up with something like maybe a dust-to-gas ratio of 8% when I start off with a 1% dust-to-gas ratio. The big caveat here, of course, is that this is actually an axisymmetric simulation. If you go to full 3D, what you often find is the formation of large-scale vortices out of this local instability. And vortices are nice because they are pressure bumps in both radius and azimuth. So you might expect some additional dust concentration. And indeed, if we redo this simulation with dust, you find the formation of dusty vortices. On the left here, this is the mid-plane dust-to-gas ratio taken from a global simulation. You see the formation of two dusty vortices. Dust is being collected and concentrated. The dust-to-gas ratio here is about 30%, a lot higher than what we had in 2D, but still nowhere near enough for planetesimal formation. And if we take a cut through the lower vortex here and see what's going on in the RZ, in the meridional plane, what we find is that the dust is actually being dispersed in the vertical direction. So the dust is actually having difficulty settling to the disk midplane due to whatever is happening in the vortex. Now, these are, as I said, taken from global simulations, but one of the limitations of global simulations is resolution. So we have recently gone back to doing local simulations, but with a global twist. So these are what we now call locally global models. If you want to know what that means, you should find me afterwards. So this allows us to go to relatively high resolution. And what we see at high resolution, first is sometimes the vortex actually disappears from the density field. You still see it in the vorticity field. It's a measure of the local rotation of the fluid. So you see this large-scale vortex in the vorticity field. Within the vortex, you see these small-scale structures appearing. So these are actually secondary instabilities that generate turbulence within a vortex that came from a pre-existing turbulent state. Now, what happens to dust in this scenario is unclear. We don't know yet, and that's sort of the next step of the project. So, very simple message here. Protoplanetary disks are vulnerable to a range of hydro instabilities. They drive turbulence that can break or make planetesimal formation. In the case of convection or convective overstability, we find the dust trapping efficiency is severely limited by the unsteady nature of zonal flows and pressure bumps. And the bigger lesson, I guess, here is that for those of us who like to use pressure bumps and vortices as sites to facilitate planetesimal formation, just remember that these structures may not be as friendly as one might hope. And I would end my talk there. If you have any questions, thank you so much.
Hi, Linkai. In your previous slide, COS requests an unstable radial entropy gradient and final cooling time, but it seems like it happened on the XY plane. But in your simulation, especially for the 2D simulation, you use 2D RZ as a symmetric simulation. Why you can catch that?
Yes. Illustrating the mechanism in the XY plane is a little bit easier to visualize, but yes, it is true that instability intrinsically is axisymmetric because it's fundamentally an inertial wave, which are axisymmetric. It really just requires it requires motions all three directions, but it can be an axisymmetric configuration. But we can talk about the details of finding this.
Hi, very nice talk. I was just wondering if you could comment on the potential effect of dust evolution on this convective overall stability.
Yes, so we did include dust in some of these simulations, and we find is that dust actually can mitigate the formation of pressure bumps. It actually opposes or discourages the formation of these zonal flows and pressure bumps for this instability.
Can I ask, do you have a quick explanation for the globally local approximation?
Yes, it's less impressive than it sounds. But it's to do with modifying the standard strain box in order to simulate this convection instability, which physically originates from the global gradient, so incorporating global gradients in local. Okay.
Thank you very much.